In this video, we'll be looking at intermolecular forces, liquids, solids, and solutions. Now, the first thing we want to think about when we're dealing with intermolecular forces is exactly what are we talking about in terms of what's happening between molecules. So when we think about intermolecular forces, we want to think about those that exist between molecules. Whenever we use the term inter, we're talking about between. Now, for this, what's happening between two or more molecules is going to be based upon what happens within a molecule. Intramolecular forces means within. So when we were talking about bonding and Lewis structures, we're talking about what's happening within a single molecule. So that's intra, within a single molecule. Inter is what's happening between two or more molecules. And what we're going to see is that what's happening within a molecule, the intramolecular forces, are going to affect what happens between molecules in terms of their intermolecular forces. And the best way of kind of thinking about this is you can think about this the same way you might think about some of your relationships with others. What's happening within a person, internally to a person, whether they are happy, sad, excited, depressed, what's happening within a single individual will affect how that person relates with others. So what's happening within a person will affect that person's relationships with others. Same thing with the molecules. What's happening within a single molecule is going to affect how that molecule can interact with other molecules. What happens within will affect what happens between. And when we think about intermolecular forces play an important role in many of the physical properties we associate with compounds. Things like melting point, boiling point, those are physical properties. Intermolecular forces play a big role in what's happening for a lot of these physical properties that we're dealing with. And generally, the stronger the intermolecular forces are, the higher the melting point and the boiling point are. It kind of makes sense, is when you boil something, you are really separating the molecules apart from each other. When you're dealing with a liquid, those molecules are in contact with each other. In a gas, they're separated by a big distance. So how do you separate those? Well, you have to input energy. To boil water, you have to input energy. How much energy is going to depend upon how strongly those particles are attracted to the other particles. And there's four types of intermolecular forces that we want to talk about: ionic, hydrogen bonding, dipole-dipole, and dispersion forces. And I listed these on this slide, strongest to weakest. And we'll start with the stronger ones. I'm not going to go exactly in this order because hydrogen bonding and dipole-dipole are related to each other. Even though hydrogen bonding is stronger, I'm going to talk about dipole-dipole first, because if you understand dipole-dipole, hydrogen bonding is much easier to understand them. So the first one we're going to look at are the ionic intermolecular force. So this is sometimes also called the Coulombic intermolecular force. Coulombs are our units for charge, so this is the ionic or the Coulombic intermolecular force. And this is what we're thinking about when we have ionic compounds. We know that there's a strong attraction between positive and negative ions. And when we're thinking about an ionic compound, we do something just like NaCl. Well, we know that the sodium is +1, the chloride is -1. What we have to think about when we're thinking about these intermolecular forces is not just one single sodium being attracted to one single chloride. Instead, we want to think about that network. There's multiple interactions between a whole bunch of different ions. And that's what we want to kind of show in these kind of cartoon level drawings. First, if we look at the one on the left, kind of a two-dimensional view of the interaction between the ions in a solid ionic compound. And what we're seeing is we're not just looking at one positive ion interacting with one negative ion. If I kind of point out one specific positive ion here, the one I'm pointing at in red, that positive ion that I'm pointing at in red is not just interacting with one negative ion. Look, it's surrounded by multiple negative ions. The same thing goes for if I point at one of our negative ions. If I point at one of the negative ions, that negative ion is surrounded by multiple positive ions. So it's not just one positive, one negative interacting. There's an entire network. The left shows this in 2 dimensions. On the right, you kind of see what's happening in 3 dimensions with this. And we're not going to get into the specific solid shapes of these crystals, but instead we just want to get at the idea that, hey, each negative ion is surrounded by multiple positive ions. Each positive ion is surrounded by multiple negative ions. And this forms a very comprehensive 3-dimensional network. Next type of intermolecular force we want to talk about is the dipole-dipole intermolecular force. And this is what you want to associate with polar molecules. When we think about a polar molecule, what are we thinking about? Well, we're thinking about the partial positive end of one molecule attracted to the partial negative end of another molecule. And the example we want to look at is Icl, iodine bonded to a chlorine. And for this, in this molecule, the chlorine is going to be partially negative and the iodine is partially positive. If you would look at a periodic table for these 2 elements, you see that chlorine is above iodine on the periodic table. That means it's more electronegative. So being it's more electronegative, it has a stronger pull on those electrons. Iodine has less of a pull on those electrons. So here we end up with partial charge distributions. The electrons are more attracted to the chlorine than the iodine. They're not ionic compounds, but instead we get these small partial charge buildups. Remember how we represent them? With the Greek letter delta. Delta means partial. The iodine is partially positive. The chlorine is partially negative. Now, if we see how these molecules are interacting, if we show this with 2 molecules, I'm just going to flip it around, what's going to happen is that the negative end of one molecule is going to be attracted to the positive end of another molecule. So the iodine is partially positive in the top molecule. It's going to be attracted to the partial negative chlorine of a different molecule. The partial negative chlorine of the top molecule will be attracted to the partial positive iodine in the bottom molecule. Again, this just shows 2 molecules. It's really a 3-dimensional network that's really happening with this. But you get the idea. We're still looking at positives and negatives being attracted to each other. There's another way we could kind of think about this. Instead of them stacking on top of each other, we can kind of think of them lining up as well. Again, we have a partial positive iodine, partial negative chlorine. Chlorine is more electronegative. In this polar molecule, it will be partially negative, the iodine partially positive. Well, that negative chloride of one molecule can get attracted to the partial positive iodine of a neighboring molecule. So this is that attractive force that we see in polar molecules. We call this the dipole-dipole attraction. We did dipole-dipole before. before we did hydrogen bonding, because hydrogen bonding is really just a special case of a dipole-dipole. And the first thing I want to talk about with hydrogen bonding is this is probably one of the most misleading names in all of chemistry. It's not an actual bond. In chemistry, when we say bond, we're really talking about the sharing of the electrons within a single molecule. That's not what we're referring to here. Bonds are intramolecular. So these hydrogen bonds aren't really bonds at all. Instead, what hydrogen bonds are an intermolecular attractive force. And really, it's just a special case of a dipole-dipole. This is a special, strong dipole-dipole interaction. It's kind of a dipole-dipole supercharge, and it only happens in specific situations. It only happens in situations when you have a hydrogen within a molecule directly bonded. Here, bonded means within a molecule to nitrogen, oxygen, or fluorine. That's the only time we can have that. So the classic example for hydrogen bonding is in a water molecule. So if we look at a water molecule, oxygen is definitely more electronegative than the hydrogen is. So on a water molecule, the oxygen will be partially negative, the hydrogen is partially positive. Well, the negative oxygen, the partially negative oxygen of one water molecule is going to be attracted to the partial positive end of a neighboring water molecule. So that interaction, just like we saw with dipole-dipole, partial positive, partial negative, is going to happen right here. There's that special strong dipole-dipole. And we have a special term for it in this case. We call this hydrogen bond, or the hydrogen bonding. It's between that partially negative oxygen in one and the partially positive hydrogen on another molecule. Just like the dipole-dipole, except we give it its own category because these are extremely strong, much stronger than normal dipole-dipole interactions, so we give it its own category. The last type of intermolecular force that we want to talk about are dispersion forces. And these go by a lot of different names. Sometimes they're called dispersion forces. Sometimes they're called London forces. Sometimes they're called London dispersion forces. Sometimes they're even called van der Waals forces. Same van der Waal from the gas chapter that we just kind of talked about, the van der Waals equation. So it goes by all these names. What they really are they're trying to talk about things that are not polar. So these dispersion forces are the weakest intermolecular force. All molecules, even if they possess one of the other intermolecular forces, will also have dispersion forces. So molecules we just talked about, ICl, NaCl, water, also will have these dispersion forces, but we're going to focus on the nonpolar compounds. Because so far we haven't seen how nonpolar compounds will actually be attracted to each other. Because so far everything's involved pluses and minuses attracting. Well, how can we get that in these nonpolar compounds? That's what these dispersion forces are describing. So generally, the larger the compound, the larger the dispersion forces for these nonpolar compounds. And the way these dispersion forces work are with what we would call an induced temporary dipole moment. Now, if we look at an atom or a molecule that's nonpolar, most of the time, you're going to have a symmetrical distribution of the electrons. The electrons are going to be evenly spaced around the atom or around the molecule. But remember, the electrons aren't stationary. They're moving around, and they're moving around kind of randomly. So what I want you to think about is taking a photograph of the electrons. Whenever you take a photograph of something, you have really frozen that moment in time. So as these electrons are moving about the molecule, imagine taking a photograph at various times. And occasionally what you would see is that those electrons would not have a symmetrical distribution. Occasionally they would be unsymmetrically distributed. This is kind of an exaggerated cartoon diagram, but here you can see on the right there definitely is not a symmetrical distribution. Well, what that means is at that one moment, that one small instant in time where you have that unsymmetrical distribution, at that moment in time, that molecule is polar. It's not permanently polar, it's not always polar, because at a different instant in time, it's not going to look like this. But at that one instant in time, you can see that unsymmetrical distribution. That molecule at that instant is polar. It would have a partial negative end and a partial positive end. So what happens is with that partial positive and that partial negative end, with what's happening within that one molecule, if there's a neighboring molecule, that's what we're seeing kind of over here on the right-hand side. How does this happen with now two molecules? So if you look at the pink molecule, imagine there's this uneven distribution of the electrons. It's temporary charge buildup. Well, in that pink molecule, there's more electrons on the left than the right. So I got a partial positive charge on the right, partial negative charge on the left. Well, what's going to happen? What happens within that pink molecule is going to induce or force a change within that purple molecule. Imagine the purple molecule starts with those electrons evenly distributed, symmetrically distributed. But as it's close to that pink molecule, it's feeling the charge buildup of that pink molecule. It's feeling that on the right-hand side of that pink molecule, there's that partial positive charge. What's going to happen then? That's going to force the electrons in the purple molecule to kind of slide over to the left. Electrons are going to be attracted to that partial positive charge. So what happens within that one molecule induced or forced a small temporary dipole moment in the other molecule. Now these are not very large, these dipole moments, and they're not permanent. They're small, they're tiny, tiny, tiny charge buildups that are temporary. And that just comes about from that random flux of the electrons. Being the electrons are constantly in motion, you will occasionally get these unsymmetrical distributions. And those unsymmetrical distributions are enough to give you a tiny little amount of attractive force even between these nonpolar molecules. So we've spent some time talking about gases previously. We should spend a little bit of time talking about liquids as well. And for liquids, there's kind of some physical properties of liquids that we at least want to kind of define and give an example of. And the first of those is surface tension. And what surface tension is this is the amount of energy required to stretch or increase the surface area of a liquid by some unit area. Almost imagine you're trying to take a square of a surface of a liquid and stretch it out. Everyone pulling on a side and trying to stretch out that liquid. And it should probably come as no surprise that higher surface tension comes from stronger intermolecular forces. And you have a little bit of exposure of thinking about surface tension is if you've ever have dove into a pool. Anytime you dive into water, you know that water is hard. There's an impact when you hit that water. And the reason why is for you to enter the water, you have to break up the surface tension of those molecules that are forming the surface of that water. Another term we want to be familiar with for liquids is viscosity. And what viscosity is a viscosity is a measure of a fluid's resistance to flow. The greater the viscosity, the more slowly the liquid flows. Stronger intermolecular forces result in a higher viscosity. Viscosity also decreases as temperature increases. Temperature and viscosity are inverses of each other. And you have some familiarity with this. If you think about some things that you kind of manipulate or do in your that you've done in the past are good examples of viscosity. The first is if you think about the oil in your car. Whenever it gets really cold outside, you're told to let your car warm up a little bit before you really drive it. Well, the reason why is that oil's job is to lubricate all the engine parts. If it's very cold outside, what that means is that there's a lot of resistance to flow. It's not able to flow very easily. So before you stress the car by driving it, what you would do is you'd let the engine warm up properly in order to make sure that that oil is able to flow everywhere it needs to flow in order to lubricate things. Kind of the best kind of imagery of viscosity is if you've ever melted chocolate before. You know that when you first melt chocolate, that it's very, very thick. If you try to pour it, it's not very runny, kind of very slowly pours out. But as you get that chocolate hotter and hotter and hotter, it becomes much thinner. It's easier to move. It flows easier. Higher temperature, lower viscosity. Lower temperature, greater viscosity. Viscosity and temperature are always inverses of each other. A couple other terms that we associate with liquids are cohesion and adhesion. When we're talking about cohesion, we're talking about that intermolecular attraction between like or same molecules. Adhesion is that intermolecular attraction between unlike or dissimilar molecules. And the properties of a lot of liquids we're familiar with is based upon the combination of these two. And kind of our first example is if we compare water and mercury. Both are liquids. When you put water in a test tube, remember that it doesn't sit flat. There is a curve to it. That curve we call the meniscus. And for water, that meniscus points up. What that means is that the water molecules are attracted more to the sides of the container than they are the rest of the water molecules. Water has greater adhesion than cohesion. The water molecules are trying to maximize contact with the walls of the container and minimize contact with itself. If you look at mercury, mercury has kind of the exact opposite properties of water. And that's because for mercury, cohesion is greater than the adhesion. The meniscus for mercury faces the opposite way. Mercury is trying to maximize contact with other mercury and minimize contact with the walls of the container. And that's the reason why mercury is not used in thermometers anymore, is because when that thermometer breaks, you get these little balls of mercury that roll around everywhere and are a real pain to try to clean up. The reason why it forms those balls is when you form a sphere, that is maximizing volume, maximizing internal contact, and minimizing contact on the outside. That kind of shows again that for mercury, that cohesion is greater than the adhesion. We should spend a little bit of time talking about our most important liquid. Our most important liquid is water, and water is a good solvent for many compounds, especially ionic ones. Kind of very important for life that it can dissolve a large amount of the ionic compounds that cells need in order to live. One of the other kind of interesting features of water is water has a very high specific heat. And what specific heat means is a high specific heat means that it is able to absorb and give off a large amount of heat, a large amount of energy without a big change in temperature. And you're familiar with this feature of water. Think about putting a pot of water on the stove to boil. It takes a long time, a lot of heat in order to get that water up to boiling. If you make ice the old-fashioned way, the exact opposite process, you have to give off a lot of heat to turn that liquid into a solid. You know that when you put water in an ice cube tray and put it in the freezer, it takes a while for that water to freeze. And that's because water has a very high specific heat. It takes a lot of energy transfer in order to change that temperature. You could contrast that with other materials you're familiar with. Most metals have very low specific heats. That means they get hot quickly, they cool down quickly. Kind of some good examples of this is if you have a fireplace, the metal tools to tend the fire. You stick it in the fire, that metal heats up very, very quickly. It'll also cool down quickly. You may have also noticed this in terms of some other things that you've interacted with. Imagine on a cold day, it's the winter. It's very cold. Your keys are in your pocket, but if you have a long walk to your car, by the time you get to the car, your keys are already cold. That metal cooled down very, very quickly. And the reason why we care so much about this idea of the high specific heat of water is this kind of tells us, this dictates a lot of our local weather. If you live near the shore, you live near a large body of water, an ocean, a sea, well, in the summer, it is always cooler there than it is farther inland. And the reason being is that specific heat of the water. Imagine it's July or August. Air temperature 90 degrees. Water temperature is not going to be 90 degrees. It's going to be much lower than that. So what that means is that water is able to suck some of the heat from the air, giving you a little localized cooling. The exact opposite happens in the winter. In the winter, your water temperature is warmer than the air temperature. And that's going to affect that local weather. Imagine it's January. Maybe the air temperature is 20 degrees. Maybe the water temperature is 40 degrees. Water is still cold, but it's much warmer than the air temperature. So that water is able to release some of that energy into the air. And what that's going to do is you get a little bit of localized warming near that body of water in the winter, because the temperature of the water doesn't change as much as the temperature of the air does. Kind of another feature of water that we maybe take for granted is that ice is less dense than liquid water. Solid ice, less dense than liquid water. Our ice cubes float. They don't sink. We kind of take that for granted because we see that happen all the time in our lives, but it's really a remarkable feature. This is actually true for very, very, very few compounds. Almost any other compound that you could think of, if you would compare the solid state to the liquid state, the solid state is almost always more dense than the liquid. But for water, it's the opposite. And this kind of plays a key role when you think about aquatic life. Imagine you're in a lake, a pond. It starts to get cold in the winter. Well, what happens is the ice forms right at the surface from the colder air, and it stays there. And then that ice forms a barrier between the much colder air and the little bit of warmer water underneath, such that your lakes and your ponds only freeze a couple inches or a couple feet on the top. And that's because ice is less dense than water. If ice were more dense than water, what would happen is as soon as it would get cold, you would start to have ice form at the surface. As soon as that ice forms, it would then sink. Now there's nothing blocking the cold air anymore, so it's going to happen. More ice forms at the surface and sinks. More ice forms at the surface and sinks. More ice forms at the surface and sinks. What ultimately ends up happening then is that you would freeze your pond or your lake from the bottom all the way to the top. That's a bit of a problem for the aquatic life in there. So the fact that ice is less dense than liquid water, we kind of take for granted. That's a really important feature of water. And all of these properties that we just talked about with water, almost all of them have to do with the three-dimensional hydrogen bonding network in water molecules. Water molecules are one of the best molecules at hydrogen bonding. We know hydrogen bonding is a very strong intermolecular force, and that specific three-dimensional arrangement is what gives us a lot of these properties of water that we're used to seeing. We also want to talk a little bit about some solid properties as well, and mainly the two different types of solids that we have. So we can have amorphous solids or crystalline solids. And amorphous solids lack a regular three-dimensional arrangement of the atoms or the molecules. A good example of an amorphous solid would be something like glass. Meanwhile, a crystalline solid have a regular repeating structure. And good examples of crystalline solids would be something like a salt. NaCl or diamond would be good examples. And if we were to zoom in and go into the molecular level, if we were able to zoom in that far and see how the molecules or the atoms are arranged, what we would see that in that amorphous solid, you see there's a randomness there. Whereas in the crystalline solids, there's a regular repeating pattern. Amorphous solids are almost like a super thick liquid. Occasionally, just in the vibration of the molecules, they can change place a little bit because there's room for some of them to fall in different places. Crystalline solids, every single molecule is in a very specific position. It is regular, it is repeating, there's no changing that can happen for that. I'll talk a little bit about phase changes, so going between solids to liquids to a gas, or a gas from a liquid to a solid. So what this diagram represents is a phase change diagram. So what this phase change diagram does is it kind of shows, imagine taking a solid and supplying to that solid steady heat, a steady heat source. And what we're going to see is we're going to track through the changes that are happening to that solid. So imagine we're kind of down here at the origin. We're at a low temperature, we grab our solid, we start supplying heat to that solid. Well, what's going to happen? As we supply heat to that solid, we're going to see that the temperature of that solid increases. Eventually, we'll get that solid hot enough to melt. Now, in the process of that solid melting, we're still supplying heat. But notice that we're at a horizontal part in this graph. The temperature isn't changing at this point because what's happening is that extra heat that we're supplying isn't going to increase in the temperature. Instead, it's going to bring up those intermolecular forces to transition between those stages. So keep supplying the heat. No temperature change. It's a flat part on the graph. Eventually, you will melt all of that solid, so you'll have a liquid. Now, as you have that liquid, as you're still supplying heat, what you'll notice is that the temperature of the liquid will increase. Keep supplying heat, temperature keeps going up. Eventually, you will start boiling that liquid. So you're transitioning now between a liquid and a gas. notice that when you're boiling that liquid, there's no temperature change. You're at a flat part on this graph again. The temperature isn't changing. Why? Because the heat that you're supplying isn't going to the temperature, it's going to disrupting those intermolecular forces, separating out those molecules from the liquid stage, getting them far apart where they're really not feeling a lot of that attractive force. That's going to take energy. That's where that heat is going into. Eventually, as you are boiling that liquid, you'll get all that liquid converted to a gas. Now, if you take that gas and keep adding heat to it, we know what's going to happen. Temperature is going to increase. So the key parts to this is recognizing that at the phase changes, you're at a horizontal part on this graph. The temperature is not changing when you're actually undergoing the transitions. So we showed this from a solid melting to a liquid and then vaporizing or boiling to form a gas. Well, you could do this the exact opposite way as well. You could start with a gas, cool it down. Instead of a heating curve, it's kind of a cooling curve. You have your gas, you're going to cool it down to form a liquid, then you're going to take that liquid and form a solid from that. Same thing whether you're heating or cooling, those phase transitions will always occur at a consistent temperature with no temperature changes present. So next up, we want to look at a phase diagram. And what a phase diagram is the complete description of the temperature and pressure conditions at which a substance can exist as a solid, liquid, or a gas. Basically, it's a graph form of a whole bunch of data. Imagine a big table of data, a whole bunch of temperatures, pressures, and then is it a solid, is it a liquid, or is it a gas? It would be very cumbersome to look at that big table of data. Instead, you kind of turn it into a graph form. And we have two phase diagrams shown. On the left, you have water. And what you'll notice on a lot of these phase diagrams is what's called the triple point. And the triple point is a set of conditions in which all the phases are in equilibrium with each other. And if I circle the triple point on the water graph, it's point A there. If you were at that exact temperature and that exact pressure, what you would see is that if you had a sealed chamber at that temperature and that pressure, all the different phases of water, solid, liquid, and gas, would be in complete and perfect equilibrium with each other. They would exist that way indefinitely. Now, we're not used to seeing that because the triple point for water is at a much lower pressure than what we're used to. You know, where you operate close to 1 atmosphere, it's much lower than that. So we're not used to kind of seeing that for water. What we're used to seeing for water is usually we're operating close to or at 1 atmosphere of pressure. So if we're at 1 atmosphere of pressure, we have a solid, then we transition to a liquid, then we transition to a gas. We don't really see solid and gas be in equilibrium with each other. If you look at the phase diagram on the right, though, for carbon dioxide, if you look at it for the right in carbon dioxide, I kind of plotted out what 1 atmosphere looks like. We kind of plot through 1 atmosphere here, highlighting this in purple. We'll notice that we go directly from a solid to a gas. We don't hit the liquid stage. That transitioning from gas directly to a solid, sometimes we call that sublimation. And for this, when we are looking at this, we don't have liquid CO2. It goes right at 1 atmosphere. It goes right from a solid to a gas. We don't hit the liquid part of that just based upon where this is at for 1 atmosphere. You're familiar with frozen CO2. Frozen CO2 sometimes called dry ice, sometimes used to help ship perishable foods to keep them cold. So if you've ever ordered something that had to be kept cold, you'll notice that sometimes they pack it in dry ice. And if you've ever watched the dry ice, you know that it just kind of evaporates. It goes right from a solid to a gas without ever becoming a liquid. We've already spent a little bit of time talking about solutions in previous units, but we want to go back and touch on some other things that happen with solutions, because as we're talking about liquids and solids, solutions certainly play a role in that. So just some other additional things to talk about for solutions are some different types of solutions that we have. And we can classify these by concentration. So we're not getting into any sort of calculations. We've already dealt with molarity previously, but more some qualitative terms that get used in describing solutions that we want to make sure we are familiar with. So the first type of solution that we could have is a saturated solution. A saturated solution contains the maximum amount of solute that can be dissolved at a given temperature. No more solute could dissolve. If you tried to dissolve more, you couldn't get any more to dissolve. Unsaturated just means not saturated. So this contains less than the maximum amount of solute. More solute could be dissolved in that solution. There's one last type of solution that we're going to mention, and that's called supersaturated. And a supersaturated solution contains more solute than a saturated solution. So when you look at this, well, how can that happen? Because we already said saturated contains the maximum amount. How can you be over the maximum amount? Well, what saturated means is the maximum amount that can be long-term stable in there. If you have a saturated solution and you cap it up, it will stay there indefinitely till the end of time. That solid will not fall out of solution. You can sometimes go over the amount in the short term though, and that's what we mean by a saturated solution, or a supersaturated solution. You can, in the very short term, get more solute to dissolve than a saturated solution. It's just that these are very unstable. Pretty much anything can make that extra solute come out of solution. Sometimes just moving it, touching the beaker, any sort of vibration will cause that additional solute to come out of solution. So for a short amount of time, you might be able to go over the saturation point and make it supersaturated, but it's not long-term stable. When we think about solutions, we often use the idea of like dissolves like. And what that means is that similar polarities will dissolve in each other, and polarities that are not similar to each other will not dissolve in each other. Polar solutes will tend to be soluble in polar solvents. Nonpolar solutes will tend to be soluble in nonpolar solvents. Polar dissolves other polar, nonpolar dissolves other nonpolar, but polar and nonpolar are not going to mix. And you are pretty familiar with this idea of like dissolves like in terms of polarity. You've experienced this quite a few times in your life. You can dissolve sugar or salt into water. Water is very polar, sugar's polar, salt very polar, they dissolve. But oil and water don't mix. Oil is very, very non-polar. Water is very polar. So those don't mix. They separate out. So you have some experience with this idea of like dissolves like. The bottom, we aren't going to do any calculations with these, but we just want to briefly mention some different concentration units that get used. We've already dealt a lot with molarity previously, but there are other ways you can express how much solute is dissolved in the solvent or how much solute is in that solution. We're not going to do any calculations with these, but occasionally you hear these mentioned for, very specific things that you sometimes have to do. So I just want you to be familiar with there are other ways of expressing concentration besides molarity. And that could be things like mole fraction, as a weight percentage, or something called molality. We're not going to go into any of the details about any of those. We just want to mention them as other ways of describing concentration. I'm going to talk a little bit about how temperature can affect solubility. And for this, it depends upon what the solute is. Is your solute a solid or is it a gas? We're going to start with the solid. Most solids have an increased solubility as temperature increases. And you have some experience with this. You can dissolve a lot more sugar into hot water than you can cold water. And you know that. You've known that since before you even took a chemistry class. You can get a lot more sugar to dissolve in hot water than cold water. Why? Well, as you increase the temperature, you're increasing the molecular motion. And we want to think about what has to happen for something to dissolve. For something to dissolve, you have to have the solvent molecules surround each individual solute particle. So the more molecular motion that you get at higher temperatures gives you more motion. That makes it easier for the solvent to surround the solute. Now, if your solute is a gas, you have the exact opposite property happening. Most gases have a decreased solubility as temperature increases. And again, this is something that you're familiar with. If you think about a carbonated beverage and the process of that carbonated beverage is going flat or losing that carbonation, you know that a warm carbonated beverage will go flatter faster than a cold carbonated beverage. You've experienced this before. And the reason being is that as temperature increases, the gas has an easier time breaking through the surface of the liquid, allowing the gas to escape the solution. So in this kind of cartoon level diagram on the bottom, the X's represent the solute particles that are gas. Now, when these solute particles come up to the surface of the liquid, two things can happen. They can either have enough energy to break through, or they don't. If they don't have enough energy to break through, it's kind of like hitting the wall of a container. They just get reflected back down. But if you have more molecular motion in this case, the gases are going to be moving faster. If that happens, more of them are going to have the power to punch through and break that surface of the liquid. And once they've escaped, they're not coming back in. Your carbonated beverage doesn't spontaneously recarbonate after it goes flat. So the more energy you give this system, the more of these gas particles, the easier time these gas particles are going to have breaking through that surface of the liquid and ultimately escaping. Pressure also will have an effect on solubility, and this really only matters if your solute is a gas. And for this, the greater the pressure of the gas over the solution, the more of it will dissolve. And this kind of makes sense. And when you think about this, you can think about any carbonated beverage that you have. A liter of soda or a 2-liter bottle or a can of a carbonated beverage. You know that that liquid is not filled all the way to the top. They give a little space at the top of the container. And that's because they're over-pressurizing the gas in that. Here I kind of have a cartoon level diagram of this. What I'm highlighting in blue is kind of the surface of the liquid. So I have some of that solute below it dissolved and some of it above not dissolved. And we know that in this sort of situation, what's going to happen? Well, gas could escape, gas could come in. Gas could escape, gas could come in. But if I have a much greater pressure in that space above that solution, what's that going to do? That's going to force more gas to be pushed into that solution, and it's going to make it harder for those gas particles to escape. So I'll ultimately end up with more gas particles in the solution and a greater solubility. More will dissolve if I have a higher pressure. So what we just did with intermolecular forces, we want to just go through some kind of common questions, some things we use a lot of terms and a lot of ideas, but how can you use those terms to solve problems? How can you use those terms to answer questions? So I want to go through some different intermolecular force type questions with you so you can kind of see how things actually work. How can you use this information? So the first question asks, what type of attractive forces are being overcome when liquid oxygen boils at 90 degrees Kelvin? And you see it lists all the different intermolecular forces we talked about. Ionic, Coulombic force, dipole, covalent, dispersion, hydrogen bonding. So when we think about O2, and O2 going from a liquid to a gas, so what's really happening in this process? Well, we have O2 as a liquid going to O2 as a gas. So we want to think about what type of intermolecular forces are being changed in that process. Well, the first choice, ionic bonds, well, that doesn't look good. That's not even an ionic compound, so it can't be that. So you could rule that one out right away. You can get rid of choice A right away. Dipole, well, we know dipole comes from polar molecules. Is O2 polar? No, O2 is not polar, so we can't have dipole. Covalent bonds. When you're going through a phase transition, changing something from a solid to a liquid or a liquid to a gas, you're not changing the covalent bonds. Remember, the covalent bonds are within a molecule, intra. I'm not changing the bonds when we go from a liquid to a gas, so we can rule out covalent bonds there. Dispersion forces. Well, what do we know about dispersion forces? For nonpolar molecules, that's the only type of intermolecular force we have. And O2 is definitely a nonpolar molecule. So right away, we're kind of leaning towards this one, as to go from a liquid to a gas, we would definitely have to overcome the attractive forces. And what type of attractive forces does O2 have? Dispersion forces. So that one's looking like a good choice. We can rule out the last one, hydrogen bonding. This molecule does not undergo hydrogen bonding, so we could rule that one out. And we would say that dispersion forces are what's happening here. So our next question asks, which of the following substances has the strongest London force? Remember, those are the dispersion forces. And for that, the amount of your dispersion forces is based upon the size of the molecule. So we're looking at the size of the molecule. The bigger the molecule, the more dispersion forces you will end up having. So when we look at these, which one's the biggest molecule? Well, the biggest molecule out of our choices is this one. This has the most number of atoms. That would definitely be our choice for that one. Bigger molecules, more dispersion forces. So our next question asks, the concept of like dissolves like is illustrated by which of the following? So the first choice says NaCl is more soluble in CCl4 than in water. So we want to look at these molecules that we have involved here. What molecules do we have? What do we know about them? Well, we have NaCl. What do we know about NaCl? Well, we know NaCl is ionic, so that's like the extreme of polarity. So we know NaCl is polar. What other molecules do we have in place here? Well, it says CCl4. Well, what do we know about CCl4? Well, to really deal with CCl4, you can't guess whether it's polar or nonpolar. You would have to go back to things we talked about previously in order to decide whether CCl4 is polar or nonpolar. And that would involve drawing out the Lewis structure. So I'm not going to go through the whole Lewis structure process. I'm just going to quickly sketch out that Lewis structure. But when you draw the Lewis structure for CCl4 correctly, we fill in our lone pairs. So filling in our lone pairs on the outer atoms. This is what you would end up doing when you would be drawing that Lewis structure. And then, after you're happy with the Lewis structure, and this is the correct Lewis structure, and we kind of went through that one very, very fast, but that should be something you should be able to draw out very quickly at this point in your chemistry career. You would then go through the VSEPR analysis to decide whether that's polar or nonpolar. So you count those electron groups on that central atom. 4 electron groups. So that electron pair geometry is tetrahedral. The molecular geometry is tetrahedral. Bond angle is 109.5. This is, being all the outer atoms are the same, this one would be nonpolar. So CCl4 is nonpolar. Next molecule we have to look at is water. So H2O. What do we know about H2O? Well, we know real quickly that that one is polar. So now that we decided whether each of these molecules were polar or nonpolar, does that statement make any sense? NaCl is more soluble in CCl4 than in water. Is that true? Well, no. NaCl is polar. It's not going to be soluble in CCl4 at all, but it will be very soluble in water. So that first statement does not match what we're looking for that idea of like dissolves like. Now we go on talking about the next molecule. It says I2 is more soluble in CCl4 than water. So let's look at I2. What do we know about I2? I2 is nonpolar. Iodine has the same electronegativity as the other iodine. That would make this nonpolar. So now we can analyze that statement. Is I2 more soluble in CCl4 than water? Well, I2 is nonpolar, CCl4 is nonpolar, so those are going to dissolve in each other very, very well. Is I2 going to dissolve in water very well? No. Nonpolar and polar do not dissolve well in each other. So for this one, this looks like a pretty good choice here. I2 is more soluble in CCl4 than in water. That looks like a good choice to match up this idea of like dissolves like. But let's rule out the other choices. Our other choices says CCl4 is soluble in water. Is that going to be true? Well, no. CCl4 nonpolar, water polar, there's no way those are going to be soluble in each other, so we can rule out that choice. Next one says CuSO4 is more soluble in CCl4 than water. So we have a new compound to look at. Our new compound to look at is CuSO4. So that's an ionic compound. So remember, ionic compounds are like the extreme in polarity. So that one's polar. So is CuSO4 going to be more soluble in CCl4 than water? No, it's definitely not going to dissolve at all in the nonpolar CCl4, so we can rule out that statement. And the last statement, I2 is more soluble in water than in CCl4. Well, that's the exact opposite of the statement we really gravitated towards, that we really liked in green, so that's not going to be true either. So our correct answer for this one should be is that I2 is more soluble in CCl4 than it is in the water. So that's how you can kind of go through and use that idea of like dissolves like after you've identified molecules as either being polar or nonpolar. So we're just going to erase our margins here so we can look at the last question on this slide. So this asks, which of the following best explains why the normal melting point of ICl is 27.2 is so much higher than that of Br2. The molecules of both substances have the same number of electrons. So here's what we're trying to explain. We have two molecules. We have ICl and we have Br2. And what do we know about these molecules? Well, it tells me the melting point of the ICl2 is 27.2 degrees Celsius. The Br2, negative 7.2 degrees Celsius. So ICl has a higher boiling point than, higher melting point than the bromine does. That means there are stronger intermolecular forces in the ICl than there are in the Br2. So which statement best explains that? So go ahead and look through these choices. So the first choice is the chlorine atom in the ICl molecule is more polarizable than the bromine molecule in the Br2 molecule. What polarizability means is that ability, like we saw in the dispersion forces, to have that unsymmetrical distribution of the electrons. And we know that's easier the more electrons you have. So is that statement true? Well, no. One, that's not true. Bromine's beneath chlorine on the periodic table. It's bigger. Bromine is more polarizable than the chlorine. And not only is it not true, you could also rule this one out, is this doesn't have anything to do with actually explaining the feature. One, it's untrue. Two, it doesn't have anything to do with explaining what's happening. Next statement says the iodine in ICl is more electronegative than bromine in Br2. So you look on a periodic table, which one is more electronegative, iodine or bromine? Well, bromine's more electronegative. So again, this is a statement that is not true, and it also doesn't fully explain why we have this difference in the melting point. So we can rule out that statement. Next statement says ICl molecules are polar. Well, are ICl molecules polar? The answer is yes, these are polar molecules. So being these are polar molecules, what does that mean? That means we have that dipole-dipole interaction. What do we know about Br2? Well, Br2 is nonpolar. So that means we just have dispersion. So this statement, not only is it true, the ICl molecules are polar, but it also helps us in explaining why the melting points are so different. Don't just pick a true statement. Your true statement also has to mean something for addressing what you're trying to address. The ICl molecules are polar, and because they are polar, that's giving them a stronger intermolecular force than the Br2 molecules, which aren't. So right now we're kind of leaning towards that choice. Let's kind of see if any of the other choices are contenders or if we can just kind of rule those out. Next statement says the ICl molecules undergo hydrogen bonding. Well, that statement's not even close to true. That molecule can't undergo hydrogen bonding, so let's just rule that one out. The last statement says the ICl molecules have a lower molecular weight. It doesn't, and we could, sorry, it said in the question, the molecules of both substances have the same number of electrons. That means their dispersion forces are equal, so that doesn't get us anywhere. So our correct choice for this one is that our ICl molecules are indeed polar. And that does successfully explain this difference in melting points. So kind of our next question just says, which of the following phase diagrams is consistent with the sublimation of a solid room temperature, 22 degrees, and atmospheric pressure? So for this, what sublimation means is that you're going directly from a solid to a gas. So which one of these diagrams kind of represents this? So what you have to be able to do for when you're looking at a phase diagram is recognize which regions are going to be solid, liquid, and gas. They should be pretty easy to pick out. I think the easiest way to do this is kind of by temperature. The lowest region of temperature should be solid. The highest region, gas, the one in the middle, should be liquid. So I'm just going to label all of these regions on each phase diagram that we have. What's solid, what's liquid, what's going to be gas in each one of these. Solid, liquid, gas. Then what we have to do is we just need to kind of plot out what's happening at 1 atmosphere. So as we go through choice A, this first choice, I'll do this in a different color. I'll do this in purple. So we go through in 1 atmosphere. Are we going to go directly from a solid to a gas, and is it going to happen at 1 atmosphere? So our first choice, we're going across at 1 atmosphere, we're solid, then we go liquid, then we go gas. So that's not going directly from a solid to a gas. So we can rule out choice A, that does not look good. Next one to the right, okay, let's plot out what's happening at 1 atmosphere. So at 1 atmosphere, what's happening? We're going from a solid to a gas. And is that happening at about 22 degrees Celsius? Yes, so that one so far is looking good. So far this one looks like our winner, because at 1 atmosphere we are going from a solid to a gas. So right now that looks like our winner. Let's check out our other options. We go to the option in the bottom left. The option in the bottom left, 1 atmosphere, as we go across solid, then we hit liquid, then we hit gas. We don't go directly from a solid to a gas at that pressure, so we can rule that one out. The last one, what's happening at 1 atmosphere? Well, at 1 atmosphere solid, then we go liquid, then we do hit the gas, so we can rule that one out. So top right is looking at our good choice for this one. So our next question, we're looking at to provide a reason for the fact that the elements of group 7A under standard conditions, fluorine and chlorine are gases, while bromine is a liquid and iodine is a solid. So when we look at these molecules involved, what do we have? Well, we have F2, Cl2, Br2, and I2. And what we're told is that fluorine, F2, and Cl2 are both gases. Meanwhile, Br2 is a liquid, and I2 is a solid. So what can we say about this? Well, we know that solids, we have stronger intermolecular forces. So we know that I2 has the strongest intermolecular forces, and Br2 and F2 and Cl2 have the weakest intermolecular forces. But what is the true driving feature that makes I2 have the strongest intermolecular forces, making it be a solid, whereas Br2 is a liquid and the other two are gases? We want to analyze what kind of intermolecular forces we have going on here. So go down the list. Ionic, Coulombic. No, none of these are ionic compounds, so that doesn't apply. Hydrogen bonding and dipole, no. We don't have any polar molecules. Nothing's capable of hydrogen bonding. So what we're really looking at are dispersion forces. So what do we know about dispersion forces? Well, for dispersion forces, we know the bigger the molecule, the more dispersion forces we have. So which one's the biggest molecule? Well, I2 is the biggest, then Br2, then Cl2, and then F2. So I2 and Br2 are bigger, so they're going to have more dispersion forces, so more intermolecular forces. That's what makes I2 be a solid and Br2 be a liquid, while the other lighter ones don't have as much dispersion forces. that's going to leave them as gases. So that's that one. So the next one we're asked to explain is to give a reason for the fact that water is a liquid at room temperature while H2S is a gas. So when we look at the molecules involved, we have H2O and H2S. So what do we know about these? Well, at room temperature, H2O is a liquid, H2S is a gas. So that means we have more intermolecular forces in water than we do H2S. Well, what kind of intermolecular force do we have in play? Go down the list. Well, we have Coulombic. Well, no, we don't have Coulombic. It's a non-ionic compound. Both of these are polar molecules, so they both are dipole-dipole. So both of these are dipole-dipole. Same here for the H2S. But what do we know about the water? Water also has hydrogen bonding. That's special dipole-dipole. We know how strong that hydrogen bonding is. So that's why water is a liquid at room temperature while H2S is a gas. That very strong hydrogen bonding that's present in water, but not present in the H2S. So there we're looking at that second question on this slide. Now the last question on this slide says, list an example of each of the following species. So there are definitely more than one correct answer to these. What I'm going to do is I'm going to use as examples for this last question molecules that we've talked about in previous questions. You don't have to use those. Like I said, there's multiple correct answers to each one of these parts, so I'm going to use examples that we talked about in previous questions. So a molecule that contains no polar bonds. So some examples of that in molecules we've talked about in previous questions are something like F2, Cl2, Br2, okay? I2, we talked about those in 2 questions ago from a previous question on a previous slide. O2 would be another example of that. Those would all be good examples of things that contain no polar bonds. So a diatomic molecule that has both of the atoms being the same would have no polar bonds in it. So the second question, or second part to this one, says a nonpolar molecule that contains polar bonds. And again, there can be lots of correct answers for this one. I'm going to use one that we talked about in a previous question a couple slides ago. And a good example of that would be CCl4. Overall, that molecule is nonpolar, but an individual chlorine-carbon bond is a polar bond. It's just that all those polarities cancel out when you take into effect the whole three-dimensional structure of the molecule. So CCl4 is a non-polar molecule, even though the individual bonds are polar. It's just all of those dipoles cancel out like we saw in the Vesper. There are certainly other ones you could use for this. I picked this one because it's a molecule we already talked about a couple of questions ago. So the third one says a polar molecule, and there's lots of good examples of this. Again, you have a whole lot of different things that would be correct for this, but using some of the ones from that we've talked about recently in this presentation. Previous question had one, H2S, polar molecule. A couple of questions ago, we talked about ICL. So those would be good examples of polar molecules. Are there others? Sure. Are they equally correct? Sure. Just to give you an idea of writing something with that was a polar molecule. The last part, number 4, says a molecule subject to hydrogen bonding. And certainly, when you hear hydrogen bonding, The first thing I would think of would be water. Water is the classic example of hydrogen bonding. Are there other ones you could certainly write here? Sir. NH3, HF, there's a whole bunch of correct ones, but I think most of us would think about water first in terms of something that has hydrogen bonding. Certainly our most common example of that. So I wanted to do some of these questions to show you how you can use intermolecular forces that we've talked about in order to explain things, in order to answer questions, in order to do problems.